And wrapping up today, so this is the last talk of the day, and the last lighting talk at the same time will be delivered by Mateusz Brzeszcz, software developer at Adaptive Vision. His whole career he has been revolving around image processing, starting in the dark ages, that is before deep learning revolution. And Mateusz has always been focused on real-time algorithms. He is a Avid programming competitions contestant, or he was in the past, and also co-creator of the Deadline 24 marathon. And after listening to some of the Code Dive talks in the past from the viewer seat, he decided he would like to try a new perspective, the perspective of a speaker, and also he thinks that our Code Dive t-shirts are really, really cool. So he will be delivering his faster than memcpy talk. Mateusz Brzeszcz.
Okay, is it on? Is it on? Okay, it's on. So, good evening, everyone. Today I have prepared a few cases distilled from the real-life code. So, let's dive in. The first thing, the importance of measuring. So there is no fast code without profiling, as there is no correct code without testing. And the first thing that we need to do when profiling code, we need to establish some baseline. So let's be ambitious and let's get a memcpy here. Okay, it doesn't work very well. So our baseline for today will be a simple memory copy. And as you may know, there is no faster operation, contrary to what the title of the talk said, but let's see. So we copy some memory on some system. We have a 1 millisecond of time spent on this function, and then we can do some processing. Let's get an ambitious function that adds 3 to every input byte. So we test and we compare to baseline, and we have just broken the law of no thing can be faster than memcpy. We have a function that is 5 times faster. So something is clearly wrong, so let's check it. Quick disassembly. I'm not perfect in reading this assembly on the fly, but the one thing that we can see that this algorithm, so-called algorithm, is vectorized nicely, and this copy function is just a tight loop. Let's see what happened. This was tested on the Microsoft Visual Compiler. It has a nice reporting feature, so it reports what gets vectorized and what's not. So we are told that loop not vectorized due to some reason. And when we check the documentation, that reason is that this code is too simple, so there will be no vectorization, and instead we expect for memcpy to be emitted, except that no memcpy was emitted here in this code. And what's the result? The result is that the algorithm, so-called algorithm, was okay, and the benchmark baseline was flawed. So if we are measuring high-performance code, it's important to have some reference point. And what's more important is that to this reference point to be correct. Let's say you are given a task of accelerating some code, and you get this code, you work on it, you have a 50% increase in speed, but you hadn't noticed that you were testing this on the debug configuration. And of course, everything goes down the drain because this baseline was not okay. So if you push this code to production, it may be faster, it may be slower, but the result is irrelevant. And by the way, the other compiler does it properly. So yeah, that's probably a compiler bug. It's not important here. What is important that you need to check everything, even the baselines. Okay, the next case, vectorization. It's a funny one. Let's have another another thing. We have algorithm that processes images. So we go row by row, and then we process a row. We multiply by 2 every byte on the input. So the standard loop vectorization method works like that. That we process the buffer by using vector instructions, and if we are left with something at the end, a few bytes, then we process scarily because the vector instruction cannot fit in there. And let's see what we have here. This is some intrinsics, not really important. It's multiplication by 2 is implemented by adding the same value twice. Anyway, what's the result? The result, the first thing is that the compiler optimizes, the compiler vectorizes this code slightly better than we did. So it's good to rely on compiler optimization, not to write everything by hand, usually. But one thing, we have a huge performance penalty associated with processing with the scalar instructions. So if we have input divisible by vector length, everything is okay. So what can we do about it? We can do a little hack. So we don't process the input by scalar instructions, even if we are left with some reminder. We just go back a little bit, so that this last vector instruction ends when where the buffer ends. And let's test that. Okay, we have a very nice flat chart of the processing time versus width. So this nail type, but what? Okay, another thing. I have tested that in real life-ish example. An image erosion is essentially taking a minimum of neighborhood of a pixel. This is a vertical erosion, so only in vertical dimension. And if we have a boundary case, when the width is near the multiple of vector length, we can even have a 2 times speedup. Some remarks. This is not very widely used optimization, I believe, because if possible, we should treat whole image as a buffer, as a continuous buffer. So we then just fire the processing on such a buffer, and the penalty can be neglected. It will be a few instructions on the whole image, and if possible, for small buffers, when this penalty is more visible, we can just pad the memory and use, and in both these cases, we can use then the compiler-generated code, the compiler, and trust the compiler vectorizer. But one use case that's interesting, if you are writing to a part of a larger image, so you have a larger image written as a call major or row major form, and you need to write into a specific part. So you cannot pad buffer, you don't have a continuous memory. And another thing, it doesn't work for accumulators for obvious reasons. We have redundant processing. Okay, and the third one, curious case of false rank. I believe I will explain what a false rank is in a simple terms. So let's say you have 2 memory locations when you have, let's say, 2 variables, and you access these variables from 2 threads. Everything is fine as long as they don't land in a single cache line, because most processors synchronize on a cache line. So if they will land in a single cache line, then every write of variable A will will propagate through all the processor cores. Why so? We have an algorithm, a simple algorithm that produces a list of bright pixels that exceed some threshold. The important part is circled there. So we have the list is a simple std vector. So and as before, we process the image row by row, and then we process row separately. And then, okay, a simple acceleration. So we divide the input image for a few regions, and then process these regions in parallel. And at the end, we just merge this resultant vectors. Okay, so yeah, this is the. We fire that, and we see that the parallel code is slower than a single-threaded one for some given data. And why that happened? We have a separate vectors for every thread, so and every vector has its own memory storage that isn't shared for sure. And we have pre-allocated memory. There are no allocations. And what happened? Let's see how does the array of vectors look like. So the data may be separate, but we have false sharing on the metadata. So every time we push back to a vector, we need to update the my last field here. And if this code is run on 4 threads, then clearly there must be at least 3 threads that are contesting on a single cache line. And what's the solution? The solution is very simple. We just need to pad this vector. So, we just aligned this to reside for every vector and its metadata to reside in a separate cache line. And yeah, and if we run that, we have expected speedup. We don't have a for, of course, because we have some operations and so on. But yeah, the speedup is as to be expected. So that's all that I have. If there are no questions.
Thank you very much. Any questions, please? Oh yeah, why not? An applause. Thank you. And now, any questions, please? One over there, I believe.
Hi, I wanted to ask about the plot. There was somewhere mid-presentation. There was like a saw plot.
Okay.
Yeah, could you explain? Okay, that one is good. So why do we have this drop at every multiply of 32 and then suddenly rise again? Why the pattern repeats?
What's the question about which color again? Which one?
Anything aside from orange. So for the blue one, for instance.
Okay.
So why do we have this sudden drops in processing time for a certain amount and then rise again and drop again?
Okay, so this is the reason. So if we have a vector instruction, it actually takes the same amount of time on a scalar instruction. Usually, it's not always true, but usually it's true. And we can, in one loop iteration, process a lot of stuff. It takes some time. Again, lots of stuff. It takes some time. But every element at the end needs another loop iteration, and it takes a comparable time that to processing the whole vector. So this is the main reason. Because if you have back to chart, okay, here let's say we are at 32. We process the whole buffer in a one vector instruction. Actually, it's 2, but never mind. It's a technical issue. But yeah, we process this as a whole, and then if we lengthen that buffer, for example, let's go to 63. So we have one instruction that one loop iteration that processes 32 elements, and 31 loop iterations that processes one element at a time. So this is why it's slow. And why it drops at the 64, it drops right to the bottom, because it's just two loop iterations and doing the vector instructions here.
Okay, so basically the thing is that just the data is so small that the effect of vectorizing even a few elements is just rows of magnitude better than iterating over it. So if we like plotted it for, I don't know, like for instance 1,000 or 10,000 pixels, the plot would continue to have this pattern, but actually after the time it would be dominated by SIMD, right?
Yes, exactly.
Okay.
This penalty is constant on the vector length. So
yeah, okay.
And
the vectorization part will be growing.
Yeah, exactly.
Okay.
And yeah, this is what I've said here in the remarks. If you have an option of processing the whole image in a one run, it's perfect because this penalty vanishes. But it's not always true. Sometimes you have small buffers that you cannot pad, and this example that I've worked with is when you have an image and you cannot access these pixels behind some, let's say a box. You have an image, and you need to do something in a center box. This is a lot of buffers that are not always divisible by vector length.
Yep. Okay, thank you.
Thanks very much. Any more questions, please? Yeah, one over here.
Yeah, it's a follow-up. So if I understood, so the rising part was because there was like a tail for processing that was processing in a linear iterative manner. So if I'm understanding this correctly, and this is true, then why couldn't the compiler or processor execute it another using SIMD version, but with some trash data and discard the result? So why did it have to switch to the iteration back again?
First of all, the compiler doesn't know if it can access the data. Let's say you have a function and you pass the buffer of 40 bytes, and then you have memory addresses that are protected by a kernel. If you access them, there is a segmentation fault. So if you can pad the memory, that's perfect. Then you can do whatever you want.
All right, let's thank our last speaker, Mateusz Brzeszcz.